So let's take a look at section 7.3, and the title of this section is called Central Limit Theorem. So we're going to learn about this theorem that's going to help us to make estimates about a population. So the objectives here: identify the conditions needed to apply the central limit theorem. So I'm going to abbreviate and call it CLT. Use the central limit theorem for proportions to describe the sampling distribution of a sample proportion and to find probabilities. So these are our two objectives. Okay? So objectives of the central limit theorem. It's used to estimate population proportions. So if we don't know, for example, take voters. If we're trying to make an estimate about what proportion of the population is going to vote maybe for a certain candidate, this is something we can use the central limit theorem to help us make an estimate for. If some basic conditions are met, the sampling distribution of the sample proportion is close to the normal distribution. So if you'll remember back to chapter 6 when we talked about the normal distribution, this theorem is going to help us use some characteristics of the normal distribution to make some estimates. So what does the theorem say? If we take a random sample from a population and the sample size is large, and we'll talk about what that means in a second, and the population size is much larger, then the sampling distribution of p hat is approximately normally distributed with a mean of p and a standard deviation of, and the standard error that we had in the last section, same formula, p times 1 minus p divided by n. If you don't know the value of p, you can just substitute p hat. So remember that n is the sample size, and then p would be the population proportion, but this is important. We can use p hat if we don't know what the population proportion is. So as long as the sample size is large and the population is much larger, then we can apply a normal distribution to the sampling distribution. And that's going to help us make some calculations. So 3 conditions for the central limit theorem in order for the theorem to apply. Sampling has to be done randomly. So that's the first condition, is that sampling is random. So they have to tell you it's a random sample, and independent. So the elements of the sample have to be independent from each other. Okay. The sample has to be large. So how large? So we must have a large sample. How large does the sample have to be? The sample size n has to be large enough so that the sample expects at least 10 successes and 10 failures. So another way of saying that, and I don't really have a notation for expected successes, so I'm just going to kind of write expected number of successes. So I'm going to abbreviate successes, would equal n times p. So p is that population proportion, and that has to be, whatever that is, that has to be at least 10. And then same thing for the failures. So the expected number of failures needs to be n again times the complement, 1 minus p, and that has to also be at least 10. And then the third condition is that you have to have a big population. If sampling is done without replacement, the population must be at least 10 times the sample size. Okay, so these 3 conditions have to be in place in order for us to apply the central limit theorem. So let's look at an example. So the following figure shows the sampling distribution of p hat for 10,000 sample sizes, or samples of size 10, drawn from a population with a population proportion of 25%. So this was our second simulation from the last class. Remember the example with the walkers and the joggers. Note that this does not satisfy condition 2 of the central limit theorem. So condition 2 says that your sample size that you're pulling, your n, has to be at least large enough to expect 10 successes and 10 failures. Well, if my sample is only 10, that's not enough for 10 successes and 10 failures. So in this case, the sample size is too small. And so the distribution is not normal. So the central limit theorem is going to tell us, as long as those conditions are met, it's going to give us a normal distribution that we can work with. And so you can see from the picture, this really isn't a symmetric distribution. But the sample size is too small, and that's really what's causing the issue. Let's look at another example. So this was the third example of our simulation from the previous lesson. So remember, in this example, n was equal to 100. So we pulled sample sizes of 100. We did it 10,000 times from the population that had a proportion of 25%. This time, this does satisfy the sample size for the central limit theorem. And you can see that the shape of this, we said, was symmetric, almost normal. How does it satisfy those three conditions? Let's just double check. Well, first of all, it was done randomly. It doesn't say that here, but in the previous lesson, we said we were randomly drawing those samples using StatCrunch. The second condition, so let me go back one page here. The second condition said that you need to have at least 10 successes and 10 failures. The sample size has to be large enough for 10 successes and 10 failures. And so what was the expected number of successes? How would we calculate that? What would we say? We would say the expected number of successes is equal to n times p. So in this case, the p is 25%. So that would be 100 times 0.25, which gives us 25 expected number of successes. So in other words, if I pull a sample of 100, I would expect 25 people in that sample to be walkers. Remember, this was walkers and runners. And that's greater than 10. So we are good to go for that first condition. And then the number of failures, so let's write that. The expected number of failures would need to be n times 1 minus p. So in this case, that would be 100 times 1 minus 0.25, which would be 100 times 0.75. So 75% of 100, of course, would be 75, which certainly is greater than 10. Whoops, sorry about that, greater than 10. So that second condition is met. And then the third condition, remember, was that we have to have a big population. It has to be large enough to be at least 10 times the sample size. Well, remember, the sample, or the population, if you recall, was 1,000. You may not remember that from the last lesson. The population was 1,000 here. And so if 10 times my sample size, remember 10 times 100 is my sample size, the population is 1,000, and that is greater than or equal to 10 times the sample size. So all three conditions are met for us to apply the central limit theorem. So let's go ahead and calculate what the standard error should be. So standard error, back up a second, the standard error using the standard error formula. Let me go ahead and write that out here. So the standard error formula would be the square root of 0.25 times 1 minus 0.25 divided by n, which is 100, and that would be about 0.043 would be our standard error for the sampling distribution here. So what we're saying, let me make a little bit of space here. What we're saying, let me get rid of all this stuff, that the sampling distribution for this, the samples that I'm pulling, 100 at a time, 100 at a time, the sampling distribution would follow a normal distribution. So remember the notation for a normal distribution, the capital N. So the sampling distribution would be approximately normally distributed. The mean would be the 25%, and the standard error or the standard deviation for that sampling distribution would be 0.0433. Remember the notation from chapter 6 for a normal distribution. We had n and then we had mu, comma, sigma. Remember that? The first number was the mean, the second number was the standard deviation. Same notation here. So we're saying that the sampling distribution would be distributed normally with a mean of 25% and a standard error or standard deviation of 0.0433. So how are we going to use that to estimate some probabilities? Let's take a look at an example here. According to the Washington Post, in 2016, it was estimated that 36% of Americans own guns. Suppose a random sample of 500 Americans is taken. So let's go through the questions here. Who is the population that we're interested in studying? Well, we're interested in studying all Americans. So our sample was 500 Americans, and that represents the population of all Americans. Who is the sample? So those would be the 500 that we selected. Okay. Is the value 36% a parameter or a statistic? So remember that parameters go with populations. Parameters are measurements on the population. So if it was estimated that 36% of all Americans own guns, that would be a measurement on the population. So that means it would be a parameter. And since it's a proportion, we would use P. So the proportion for the population, remember, is P. So that would be 0.36. And then is the value 500 a parameter or a statistic? So is that a measurement on the population or my sample? Well, that's a measurement on my sample, so it's a statistic. And the symbol we would use, it's the size of my sample, so it would be N. N equals 500. Is the sample random and independent? As long as they put the word random in the question, we're okay to assume that. Independent as well. So we'll say yes. Is the sample large? So what they're guiding you through here are these three conditions to apply the central limit theorem. How large does the sample need to be? It needs to be large enough to expect at least 10 successes and 10 failures. All right, so let's calculate what that would be. So the expected number of successes would be N times P, so it would be 500 times the 0.36, and that gets me 180. So is that large enough? Absolutely. Remember, it's got to be at least 10, so we are good to go there. How about the expected number of failures? There's a couple of ways you could calculate this. One would just be to take the rest of the sample. So if 500 is the total in my sample, if 180 are successes, the rest would have to be failures. But we can go ahead and compute it. So it'd be N times 1 minus P. So in this case, that would be 500 times the complement of the 36%. So 1 minus 36% gets me 0.64. And if we crunch that, it gets me 320, which certainly is more than 10. So it's definitely large enough to expect at least 10 successes and 10 failures. The third condition, remember, was that the population has to be at least 10 times the sample size. Well, we can certainly assume, it's not really an assumption, it would be true. Remember, the population is all Americans, so the population of all Americans certainly would be more than 10 times 500. So yes, that is a reasonable assumption. So therefore, are the conditions for the central limit theorem met? Yes, they are. All three conditions have been met. All right, so then on the next page it says, based on the central limit theorem, complete the following table regarding our sampling distribution. All right, so what do we know? The shape is going to be normal because the central limit theorem applies. All three conditions were met. The mean for my sample proportions, so I'm using mu and then little p hat here, but you don't have to use that notation. It's going to be the same as the mean for the population, and that was 0.36. And then I need to compute my standard error. So my standard error, using that square root formula again, it's the square root, remember, of n. No, sorry, not n. Square root of p times 1 minus p divided by n. So for me, that's the square root of 0.36 times 1 minus 0.36, the complement, divided by n, which was 500. And if you put that number in your calculator and crunch the numbers, you will get approximately, let me write it down here, I'm getting about 0.0215. Okay, so then it says, what is the approximate probability? So here's the question. So let's summarize what we know so far. So what we know is that we have a sampling distribution that's going to follow a normal model. So it's going to follow a normal model. Let me write that N a little bit nicer. I'm going to use capital N for normal model. And the mean is going to be the 0.36. And the standard deviation is going to be the standard error, 0.0215. So if you remember back to chapter 6, at the end of 6.2, we talked about how to use StatCrunch to calculate probabilities for a normal distribution. That's what we're doing here. So the question says, what is the probability that the proportion of gun owners in our sample will be more than 40%? notationally, we could say the probability, so I'm using capital P for probability. I know that I'm using P again, so it's a little confusing, but that's probability that if I pull a sample, the proportion of gun owners, so P hat, in my sample will be greater than or equal to 0.45. That's what I'm trying to determine. What is the likelihood that my sample will contain, I'm sorry, not 0.45, 0.4. You're probably wondering where I got that. 0.4 from the 40% here. So I want to know the likelihood that my sample will contain at least 40% gun owners. So, all right, so on the picture, just to kind of help us get organized, I'm going to go ahead and label what I know. So the mean, remember, goes right in the middle. So there's 0.36 right there in the middle. So 0.40 is going to be more than 2 standard deviations. We'll just kind of put it over here somewhere, 0.40. So the area that I'm interested in would be this little section right over here. And so to compute that probability, this is where you're going to use StatCrunch. So you're going to go to the normal calculator, just like you did at the end of chapter 6, and you're going to put in this mean and this standard deviation, and you're going to put in your expression so that your probability is greater than 0.4. And from StatCrunch, I'm getting a value of about 0.031. So a little over 3% chance that if this information holds up as far as the 36%, that in my sample of 500 people, I will get more than 40% of gun ownership. All right, let's take a look at another question. So in a closely contested Senate race, polling indicates that 50% of voters are in favor of a certain candidate and 50% are against. Suppose a random sample of 80 voters is selected. So who is the population? So all voters, and they didn't say, it just says Senate race, so I don't know if it's a state contest or not, but we can say all voters. We'll just assume it's in the state. Could be a district, it just depends. But we'll say all voters in the state or district or whatever you want to say. Who is the sample? So the sample are the 80 that were selected. Okay. Is the value 50% a parameter or a statistic? So polling indicates that 50% are in favor. The polling is made as a general statement here. So the polling indicates that we estimate 50% of voters in the district. So for that reason, 50% will be a parameter. We'll say it's a measurement on the population. So it's P equals 50%, 0.50. And then is 80 a parameter or statistic? Well, that represents our sample size. So it's a statistic, and it's going to be represented by N. So N equals 80. What percentage of the sample, then, would we expect to favor the candidate? Well, we expect 50%, right? If the idea is 50% of the population favors the candidate, theoretically, that should be about the same for our sample. So about 50% are what we would expect. Is the sample random and independent? They did mention the word random, so we'll assume it's also independent. Is the sample large enough to expect 10 successes and 10 failures? So the expected number of successes would be N times P, so 80 times 50%, or 40, which is certainly more than 10. And so the expected number of failures, same thing. It would be 80 times the complement, 1 minus 50%, which would also be 50%. So same number, but we expect half the sample to be in favor and half the sample to be against. But they're both greater than 10. And last, is it reasonable to assume that there are at least 10 times 80 or 800 voters in the population? Yes, absolutely. So the 3 conditions for the central limit theorem are met, and we're going to ask you to check that those conditions are met. You'll see some questions like that in the assignment. So yes, that's the next question. Central limit theorem is met. So based on the central limit theorem, complete the following. So the shape of the distribution will be normal. That's the key thing right there. It means we can use our normal calculator to estimate some probabilities. The mean for my sampling proportions will be the same as for the population proportion, which was 50%. And then we need to compute the standard error. So the standard error is going to be the square root of 50% P times 1 minus P. Oops, let's write that again. Times 1 minus P. And then divided by N, which was 80. And if we crunch those numbers, I'm getting a standard error of about 0.0559. And so the question then is, what is the probability that the sample proportion will fall within 2 standard errors of the population proportion? So let's label the graph here. So the 50% will go right in the middle. That's our expected value. Our p-value is 50% of the proportion we expect to favor it. So below that would be, so if we say, okay, so our standard deviation is 0.0559. 2 standard deviations below that would put me right here at 0.3882. Make sure you see how I'm getting that. If I take my standard deviation is 0.0559. If I take my 50% in the middle, 0.50, and I subtract 1 standard deviation, let me get my calculator out. Let me get that number for you. Actually, you should get your calculator out and crunch that number and make sure you do the same thing I do. So 1 standard deviation below would put me at 0.4441. So here, let me write that on my graph just for completeness. So this would be 0.4441. Let's try that again. 0.4441. And then subtract 1 more standard deviation. And that puts me at 2 standard deviations of 0.3882. Do the same thing on the other side. So on the other side, if you add the standard deviation, add 1 standard deviation, 0.559. If you add those together, so that would give us 0.5559. So let's see. I'm trying to squeeze this in here. 0.5559, and then add 1 more standard deviation above that, it puts you at 0.6118. So 2 standard deviations below, 2 standard deviations above. That's the question. Now we could go into StatCrunch and we could use the normal calculator and we could put the numbers in, and what we would be looking at in StatCrunch, if we do that, let me write the notation out here, we would be looking at the probability that my sample of 80 voters will be between 0.3882, let me write that a little nicer here, and 0.6118. The proportion of people in my sample who support the candidate will be between 0.3882 and 0.6118, so about 39% to about 61%. We can put that in StatCrunch and get that. However, if you remember the empirical rule still applies here. So by the empirical rule, what percent of the data should fall within 2 standard deviations or 2 standard errors, because that's what the standard deviation is in this case, 2 standard deviations of the mean. The empirical rule, remember, said that 95% of the data is going to fall within 2 standard deviations. So we expect the probability that our sample will fall between those 2 numbers of support for the candidate is about 95% likelihood. That's what we're saying. So the key idea here, if the conditions for the central limit theorem are met, the probability that a sample proportion will fall within 2 standard deviations of the population is 95%. That's the empirical rule. Okay? Then it says, would it be surprising to find that 75% of the sample were in favor? Well, so think about this. 95% likelihood that the sample proportion will be between 38% and 61%. So how likely is it, do you think, or would it be surprising if we found a whopping 75%? That would be very surprising or very unusual, because that would be outside of 2 standard deviations. If you remember back to the first unit we did, we said anything outside of 2 standard deviations was considered unusual. So that's what we're talking about here. It's the same idea. So yes, since 75% is outside of 2, I'm going to abbreviate and say standard deviations of the mean.